All right, so just like with alkanes, I'm going to ask you to watch a short video at home about alkene naming. It's pretty straightforward. The main difference is you want to identify the longest continuous carbon chain that has the double bond within it. So you need to identify the longest carbon chain that has a CC double bond and then follow all of these rules. And then I walk you through a variety of examples. We also review E and Z in the video, and then I even give you a challenge one for a molecule containing more than one double bond. So how do we name these? So make sure you watch that video tonight and then complete the problem of the day. All right, so let's jump into alkene stability. And I'm going to draw a variety of different alkenes. And last but not least, I'll draw this one in right here. So on the far left-hand side, if you look at this, this is a CC double bond with one carbon coming off of it. Because of that, we call this mono-substituted. What do you think this next one's called? Di-substituted. We have two groups coming off. And then the next one is going to be tri-substituted. And then the last one's going to be tetra-substituted. These are all alkenes that we could observe. In this case, though, we need to look at the relative stability of all of these. And I'll just give you a hint, or I'll tell you directly, I should say, that it's going to get more stable as we go this direction. Why? Does anybody know why we might get more stable with more substitution?
Similar to the 1' to 3', more carbon.
So you're saying it's similar to the 1' versus 3'. When did we see that in terms of stability? Carbocations, right? Why were carbocations more stable when we had more substitution? There's a special term. Hyperconjugation. All right, so does anybody remember kind of what's going on with hyperconjugation? So in the cation example, we said we had a p orbital, and then we had an sp3 carbon right next door, right? And we said that the sp3 carbon actually stabilizes the p orbital in the carbocation. In this case, we also have a p orbital right there, right, in the double bond. And then right next door, we've got an sp3 substituent. That means that the sp3 substituent is actually going to stabilize that p orbital slightly. It's not as strong as resonance, like we saw previously, but it's reasonably strong. And in this case, we can actually see these stability trends when we do reactivity tests. So for example, which one do you think it is going to be the most reactive as a double bond? Mono-substituted. And we'll actually see that when we get into the next chapter at the start of January. All right, there's one other area I wanted to hit. And this is cis versus trans. We talked about this briefly, but what does cis mean again? Same side. All right, so let's take a look at this one. And I'm going to draw in all of my hydrogens just so we have some clarity here. So this is cis in two different ways, right? It's cis because the hydrogens are on the same side, and it's cis because the methyl groups are on the same side. So this would be cis. Let's compare this to trans. In this case, trans has each of these groups on the opposite sides. Which of these is more stable and why? Why trans? I hear a lot of people mumbling and moving their hands in the air. I like it. Like, you know, just...
That's the answer.
Well, let's think about it this way, right? This looks kind of like what we saw in our Newman projections, right? This kind of Gauss-like interaction where these large groups are brushing up against one another. So this is destabilizing. Which means that trans are actually going to be more stable. And cis will be less stable. This is kind of interesting when you think about it, because when you think about natural fats, which double bonds are found in natural fats, cis or trans? So trans are the unnatural ones. That's the stuff that causes heart disease. So cis fats are actually natural. Trans fats are unnatural. However, our body makes, for whatever reason, the less stable alkene when we produce fats or ingest fats from a plant. So it's a little bit weird that way, but it's important to remember that cis alkenes are less stable than trans alkenes. All right, so now what we're going to do is we're going to change gears and look at how to make alkenes. And this will tie a lot into the chemistry we learned previously about substitution. So let's do method 1. Actually, sorry, I'm going to change this a little bit. Never mind. We'll do method 1 here. I'm trying to change things on the fly, but now I don't want to. Method 1, we've got a leaving group attached to a carbon. Is this a primary, secondary, or tertiary carbon? It'd be a secondary carbon. Okay. And then we've got a base. So instead of a nucleophile, what we're dealing with now is a base. Specifically, this base has a negative charge, so is this going to be a strong or a weak base? Strong. So it's probably going to be a strong base. And then let's go ahead and look back at our starting material with our leaving group. There's a few things we need to look at. First thing is we need to look at the carbon where the leaving group is attached. We said that that's this carbon right here, and we said that it's secondary because it's attached to 2 other carbons. This carbon actually has a more specific name. This is called your alpha carbon. Your alpha carbon is directly attached to your leaving group. What do you think we call the carbon right above it? Beta, exactly. And in this case, we actually have 2 different beta carbons, so it really doesn't matter which beta carbon we're looking at. And off of these beta carbons, we have 3 different hydrogens. This becomes very, very important with these reactions. So I'm just going to draw in all of these beta carbons. So what happens in this reaction is your base will reach over and grab one of these beta protons, and then like a series of dominoes falling over will kick off our leaving group. So this is a 3-step arrow pushing process. So when we do this, we form a new double bond. Let me clean this up a little. Between our alpha and beta position. Students will often ask, well, what if we did this one with the green arrows? Well, let's consider that. Well, if we did that one, then our double bond would be down there and we get a single bond there. What's the relationship between these products? It's the exact same thing, right? So it doesn't really matter which of the beta protons we choose. However, as we'll see later on in this chapter, if we've got more than one type of beta proton, we need to consider the possibility of getting multiple products. In this case, we only get one product. All right, and then we get our conjugate acid, and then our leaving group is going to fall off just like it did in our substitution reaction. So now let's get back to the idea of the strong base. Why do you think we need a really strong base for this to occur? Let's think about what we're deprotonating. We're deprotonating a proton coming off of a carbon. Are protons that normally come off of carbons very acidic? Why or why not? Let's think about the cardio rules, right? We said in the cardio rules that protons coming off of electronegative atoms tend to be most acidic, right? Is carbon a very electronegative atom? No, so it doesn't really want to give up its proton. So what I'm going to make is a note down here that the strong base is required to deprotonate. If we have a weak base, that proton coming off that carbon just really isn't going to get removed very readily, right? So in this case, we need to use a stronger base. All right, let's think about the rate of this reaction. What do you think the rate limiting step is? So try to describe what's rate limiting. Do you think the rate limiting step is the leaving group falling off, or do you think it's the concerted deprotonation and leaving group falling off? It's the whole thing happening at once, right? So let's make a note here that the note is the rate limiting step involves the base and our reagent with the leaving group. What does that tell us about the reaction order? Is it going to be first, second, or third? What do you think? Second order reaction. So in many ways, this kind of looks like our SN2 reaction, right? Where in our SN2 reaction, our nucleophile hit that carbon the same time the leaving group falls off, so it's second order. And in fact, we can even come up with a rate equation for this. So the rate is going to be equal to our rate constant times our concentration of our thing with our leaving group times the concentration of our base. So this would be a second order reaction. Just like with an SN2 reaction, we can name this, and this is called an E2 reaction. So if we look at the E stands for elimination, and the 2 stands for second order. All right, just for fun, if we were to draw a reaction coordinate diagram for this, would it have one hump or two humps? Just one hump, right? Because it only goes through one step as we go from starting material to products. So this makes sense. Let's consider another method. So this seems reasonable. Does anybody have an idea for what could occur in the second method? And let's think about what we saw in substitution chemistry. What do you think? Ooh, Jade asked a really good question. Why doesn't the leaving group fall off first? Well, let's consider that as a second possible method, right? So if we think about method 2, Jade says, what if the leaving group falls off first? Well, let's consider what sort of starting material we would need with a leaving group. So if we think about what would go in this box over here, and then our base over here, let's try to figure out what would go in this box. Should it be a primary, secondary, or tertiary carbon if we're going to assume that the leaving group falls off first? So tertiary would work better. Okay, so tertiary carbon we know would favor that leaving group falling off first. So let's consider this as an option. So I'm just going to show the leaving group falling off. Sorry, I'm going to move my base over a little bit. And let's say that's our first step. This is favorable because we get our tertiary carbocation, which is relatively stable. It's not great, but it's relatively stable. And then we have our leaving group with the negative charge. All right? Now we need to ask ourselves, okay, well, where is the alpha position? This gets a little bit weird, but our alpha position is going to be our carbon with the positive charge on it, right? So the alpha in this case is going to be our carbocation carbon. Beta is going to be one further away. Okay, so we've got beta here, beta here, beta here. And just like before, we've got protons coming off of these beta positions. You could show all of them if you want. I'm just going to pick one of these methyl groups because the other two methyl groups are pretty much identical. All right, let's think about what could happen in the next step in order to give an alkene. What do you think could happen? What do you think? Yeah, it's going to snatch one of those hydrogens, or protons to be more specific, and create a double bond. Snatch being the scientific term. All right, so we're going to take one of those and we'll get a double bond out. Just like before, it doesn't matter which beta proton we select, we're always going to get this product. And then over here, we're going to get a leaving group with a negative charge. All right, so now what I want to do is I want to look at the base that's used here. So in the first reaction that we saw, just one second. In the first reaction that we saw, we said we need a really, really strong base. In the second one, do you think we need a really, really strong base?
No.
Why not?
No.
Because the carbocation's so unstable, even a weak base could accomplish this. So let's make a note. Only a weak base is needed because the carbocation is so unstable. All right, Mohammed, what was your question?
So, why you always choose this hydrogen from that base?
That's a good question. So we'll talk about, you were asking why are we always choosing the proton that's furthest away?
Yeah.
We'll talk about that in a few more minutes if we have time. We have to be very careful which beta proton we choose to deprotonate, but we'll get to that next. Yes, and I'll talk more about the details. We'll actually go back to Newman projections, believe it or not. Yeah.
Does it always have to be a weak base? Or can we use a strong?
That's a good question. So for this mechanism to occur, typically a weak base is preferred. What do you think could happen if we have a strong base? In fact, let's do that over here. So let's say we have a base with a negative charge that's a lot stronger. Well, let's think about this, right? We still have beta protons over here. If we have a really, really strong base, it could just go ahead and do this all in one step, right? In which case, this wouldn't be a reaction that we're going through a carbocation with. So really, we only observe this mechanism where we have that carbocation intermediate when we're dealing with this relatively weak base. Otherwise, we'll actually get the competing mechanism that we just covered. Yeah, that's a good question. All right, so now let's think about the rate limiting step here. What's the rate limiting step? Yeah, the rate limiting step involves the leaving group falling off. All right, so that tells us something about the reaction order. Is this going to be first, second, or third? First order reaction. All right, and just like before, we can actually find the rate of this reaction, where the rate is going to be equal to just our starting material with the leaving group. The base isn't actually involved in that rate limiting step, right? So when we go ahead and we describe this reaction, it's still an elimination reaction, meaning we're making an alkene, and the next number would be 1.
Nucleophile.
Yeah, so Eric's question is, in SN1 and SN2, we had that subscript N,
Right.
indicating that it was a nucleophilic substitution. There's actually other types of substitution in chemistry that aren't nucleophilic substitutions. We just don't cover them in our textbook.
Okay, but this is the only type of elimination?
Yes, this is the only type of elimination, so we don't need to worry about a subscript.
Okay.
Yep, good question. All right, so as we look at this, you can kind of see method 1 has a lot of the characteristics that we see in SN2 reactions, right? It's one step. Method 2 has a lot of characteristics that we saw in our SN1 reactions, meaning it's 2 steps. If we were to draw the reaction coordinate diagram for this, how many humps would it have? It would have 2 humps, right? So there's a lot of analogous things going on. All right, so let's take a look in lab. All right, so in lab, if you have lab either this Thursday or this Friday, we're going to be working with an alcohol, cyclohexanol, and we're going to treat this with a catalytic amount of acid. So I'm just going to call this H+, catalytic acid. And the product of this reaction is going to be an alkene. So we know that this is going to be an elimination reaction. And then our byproduct for this reaction is going to be water. So this is going to be our net reaction. What happens to the catalyst during this reaction? Nothing. It's going to be regenerated at the very end. So let's try to propose a mechanism. All right, so if we think about this, can the leaving group fall off first? Why not? It's a terrible leaving group. So at this point, we would look at this and we would say, well, this is a bad leaving group. In addition, we don't even have a base around to do an elimination, right? We have acid. So no elimination is going to occur during this first step. What do you think could happen during this first step? Yep, so you said that the lone pair from the oxygen could reach out and grab the proton from the acid. I agree. Acid-base chemistry is very, very fast. So in our next step, we're going to have this alcohol that's now protonated, which is pretty good because now it's a good leaving group. Okay. We still don't have a base around though, so do you think we're going to do an E2 reaction, or what do you think is going to happen? Let's try to make sense of this. So we have no base, that means it can't be E2, which means it must be E1, right? So what occurs in an E1 reaction? Leaving group falls off. All right, so let's make sense of this and predict what will happen. In this case, the leaving group will fall off first. It'll give us this carbocation. Okay, so now we've got water kind of floating around. I'll include my lone pairs here just to be thorough. We said that it won't do E2 because we don't have a strong base around at all during this step. Okay, now what do you think will happen? Well, let's think about it, right? We've got an alpha position right here. We've got beta and beta that's right next door. We've got beta protons coming off of either of these positions. And if we think about water over here, is water a strong base or a weak base? Weak base. Well, why would it be able to do this elimination reaction if it's a weak base? Because the carbocation is so unstable, we can get away with using a weak base, right? So if we think about the next step, it could grab any one of these beta protons and give us a double bond. And then we would regenerate our acid in the end. So the acid is regenerated. So even though we're looking at this and it involves more than 1 or even 2 steps, why are we classifying this as an E1 mechanism? Because the leaving group falls off first, exactly. So this is E1 because the leaving group falls off first. So there's a lot of analogies to what we've seen previously, right? So in our chapter about substitution, we said if we have an alcohol, we need to turn it into a better leaving group. We can do that one of 2 different ways. We can either protonate it, like we're seeing here. What was the other way we could do? Tosylation. If we tosylate it, then we could treat it with a strong base and accomplish the same transformation. What do you think the benefit is of using acid here?
Get it back in the end.
Yeah, exactly. It's catalytic. We get it back at the end. So in this case, it's a greener reaction by using catalytic acid rather than tosylation, which has a low atom economy. So we'll run into this a lot. What's another thing we might need to watch out for in an E1 reaction that we had to watch out for in an SN1 reaction? Rearrangements, right? So just like before, anytime we form a carbocation, we need to watch out for rearrangements. Why didn't one occur here? Yeah, there's no way to make this into a tertiary carbocation, so we didn't have to worry about rearrangements here, but there might be situations where we do. Does that make sense? Okay, so now let's kind of compare substitution to elimination. Whoop, that's not what I want. Okay, so substitution, we had SN2 followed by SN1. And in an SN2 reaction, we said that we would have something like this with a nucleophile, and the nucleophile is just going to reach out and kick off our leaving group. Right? So this would be a classic SN2 substitution reaction. SN1, it's going to be a little bit different. In an SN1 reaction, your leaving group falls off first. And then your nucleophile will attack in to give us our new product. All right, so if we look at this reaction, right? How many moles did we put in? Meaning how many moles of different reagents? Okay, so on the top we put in 2 moles, and it went to 2 moles. Over here we did 2 moles, and in the end it went to 2 moles. What does that tell you about delta S for these systems? It's going to be close to 0, right? Meaning there's not really a net change in the disorder for substitution reactions. All right, now what I want to do is let's do elimination underneath. Sorry, I'm going to spread this out so we can see everything. And up here we'll do E2. In the E2 example that we saw, we had to have a really strong base. So I'm going to have a negative charge on that. And then we said we need to grab one of these beta protons, meaning protons coming off of the carbon that's 1 further away from our leaving group. And let's do E1 immediately underneath. This time we don't need a strong base, but our first step is going to be our leaving group falling off. And then just like before, we need to find beta protons. In this case, it's going to be a proton that's 1 further away from our carbocation. Zoom out a little. All right, so now let's consider delta S for these, right? So let's look at the E2 reaction. In the E2 reaction, we put 2 moles in, and we got how many moles out? 3 moles. If we look here, we put 2 moles in, and in the end, same thing. So if we think about delta S of the system for elimination reactions, is it going to be positive or negative? positive. Okay, this is interesting, right? Or maybe it's not. Up here, we said that there was no change in entropy. Really, it's going to be close to 0. On the bottom, we said delta S of the system's positive for the bottom one. All right, I have a question for you. Do you think elimination's going to be favored under high temperature or low temperature? Check with your neighbor. All right, so let's maybe reconvene as a class really quick. Let's do the substitution example. So if delta S is approximately 0, what effect does changing temperature have on delta G? Really minimal to no effect, right? So changing T doesn't really impact delta G for substitution. All right, now let's think about this one. Over here, we said that delta S is positive or negative? Positive. All right, which tells us something. What is this whole sign right here? It's negative, right? All right, so let's think about what happens if we really, really increase T. So if we increase temp, what happens to delta G? Delta G gets more negative. Is that a good or a bad thing? Why is that a good thing? It's more spontaneous. All right, so this is kind of an interesting takeaway from this. Changing temperature has no impact on substitution reactions. We could crank up the heat, it doesn't really change much about the reaction outcome. But with elimination, it has a large impact. Yep.
Changing heat doesn't really impact, right?
Oh yeah, sorry, holy cow. Let me fix this. This should be doesn't. Doesn't really impact delta G, thank you. Yeah, yep.
What about change of edge, like,
So you're saying what impact does changing delta S have?
no, like delta H?
Oh, delta H. Yeah, that's a good question. So if we think about delta H, that sign does matter, but equally as important is this half of the equation, right? So we could really, really, really crank up our temperature to the point where that will overcome the enthalpy portion of the equation. So it doesn't really matter what the sign is for delta H. We know that when we increase temperature to a high enough point, that the reaction will at some point become spontaneous, meaning delta G will be negative. Yep, it's a really good point. All right, so this is the big takeaway. Is eliminations, meaning elimination reactions, are favored at high temp. Because we want to increase the disorder of the system. We want to take advantage of the entropy change, right? So we want to get our 3 moles out compared to the 2 moles that we put in. So that's a big, important difference between substitution and elimination. All right, so let's continue on to the next thing. Because if we go back up here, It looks pretty confusing. If we look at SN2, we've got a nucleophile with a negative charge attacking your carbon with the leaving group. With an E2 reaction down below, we've got a base with the negative charge. But in this case, it's not attacking the carbon with the leaving group, it's doing acid-base chemistry. This gets confusing. So how do we define what's a nucleophile versus what's a base? And it's not an easy thing to distinguish, but we did talk about it briefly last chapter. So let's review. We'll do good nucleophile over here, and then we'll do a good base over here. So how do we define a good nucleophile? Is a good nucleophile something that's stable or unstable? Okay, so a good nucleophile is unstable. All right, what was the other thing we looked at with nucleophiles? What is that? Not bulky. Perfect. So these were the two key things we look for when we're finding a good nucleophile. All right, there was another way that we could change the strength of a nucleophile. Does anybody remember one of the other things we looked at? The solvent. So if we think about a good nucleophile, is it favored in polar protic or aprotic solvents? Okay. Right, because that destabilizes our nucleophile, makes it a better nucleophile. All right, let's consider our reaction coordinate diagrams. So we've got energy here, we've got our reaction progress down here. If we think about a good nucleophile in an SN2 reaction, are we really concerned about our activation energy, or do we care about our delta G? What do you think? Activation energy, exactly. So with nucleophiles, what we're really trying to do is we're trying to make that hump as small as possible so that the reaction will go faster. So a good nucleophile will have a small activation energy. All right, now let's go over and consider what makes a base a good base. Is a base going to be good when it's stable or unstable? Unstable. So a good base is unstable. All right, let's think about size. Does size impact basicity? Did we look at size at all during our acid-base chapter? No. So size doesn't matter. What about solvent? Does solvent matter a whole heck of a lot for bases? In fact, we had a whole page in our acid-base chapter where we said that the solvent's ideally going to be inert or non-reactive during acid-base chemistry. We don't want it to do anything. So down here we would say that solvent plays little to no role in acid-base chemistry. So there are some differences, right? The thing that confuses people is this part where they say, well, a good base is unstable and a good nucleophile is unstable, so aren't they the same thing? Not necessarily. What if we have something that's unstable and quite bulky? It would be a good base, right? Would it be a good nucleophile? No. So we can kind of find these little paths where we can find something that's a good nucleophile that isn't also a good base. And so we'll come back and talk about that. However, before we do, let's do our reaction coordinate diagram for this one. So let's think about what matters for acid-base chemistry. Are we looking at activation energy or delta G? Delta G, exactly. So good bases have a large negative delta G, right? What about the activation energy? Do we care about activation energy for acid-base chemistry? No, not at all. Acid-base chemistry, all we care about is delta G. We don't care about the activation energy. So while these are kind of related, they're very, very different in that regard. All right, so let's go on to the next part. So factors that affect activation energy. Another way of thinking about this is factors that affect nucleophilicity. First thing we said was stability. All right, and it's important to note that this is impacted by solvent. All right. So we know that it's better if we have things that have a negative charge. So what I'm going to do is I'm going to make a mini periodic table of negative charges. And we're going to focus on the best part of the periodic table. We're going to ignore all those silly metals. So while I'm showing carbon with a negative charge, it's not just carbon by itself. It's assumed that that carbon would have other things on it, right? All right, so let's think about going left to right across a row. Which side is going to be less stable and why? The left side is going to be less stable. Why? Okay. It's going to be less stable due to electronegativity, right? Carbon's not a very electronegative atom. It does not want that negative charge. So really, if we're going left on the periodic table across a row, we're getting to things that are less stable, meaning they're going to be more nucleophilic, right? Over here, we would get to more stable. All right, now what I want to do is go up and down columns. And first thing we're going to look at is aprotic solvents, meaning solvents that can't hydrogen bond. Do things get more stable as we go up? Or sorry, which direction is going to be less stable? Let's change it that way. Well, check with your neighbor and see if you agree. Which side is going to be more stable? Which side is going to be less stable? All right, so let's check. Raise your hand if you think fluoride is less stable. So we're thinking less stable now. All right, so it looks like most hands went up. Why is fluoride going to be less stable in an aprotic solvent? What do we look at when we're going up and down a column? Size, right? So it's small. It's forcing that negative charge into a really small atomic radius. That means that it's less stable. And down here, the iodide is going to be more stable. So in an aprotic solvent, we get less stable as we go up a row. All right, let's consider a different solvent, though. What about with protic? What happens to the trend when we switch to protic? It's going to be reversed. So we get less stable as we go down and more stable as we go up. So we can actually impact nucleophilicity by changing the solvent that we're running our system in, right? Why do things get less stable as we go down a row? Or conversely, why do things get more stable as we go up a column in a protic solvent? Hydrogen bonding, right? So it's going to really form a tight solvation shell around fluoride, where iodide, being this giant atom, isn't going to be wrapped up by solvent as much. All right, so stability trends are kind of things we're familiar with. Next thing we looked at is sterics. That's a fancy word for bulkiness. All right, so let's look at sterics. And I'm going to consider a few different oxygen atoms here. If we think about these in terms of stability, do you think they're going to be the same or different? Stability, not bulkiness. I'd say according to the cardio rules, they're about the same, right? They're all oxygens with a negative charge, no resonance, no significant dipole induction. All right, but now let's focus on bulkiness. Quite apparently, this one's most bulky. Is this one going to be a very good nucleophile? Okay, so let's come up with a trend for this one. More bulky equals bad nucleophile. Less bulky equals good nucleophile. So you said that OH negative is a bad nucleophile?
You've already said that OH is a bad nucleophile.
Not quite. I'd say OH negative is a pretty good nucleophile, right?
Oh, it's a bad leaving group.
It's a bad leaving group.
Yeah.
Exactly. All right.
Thank you.
Conversely, let's think about basicity. Which of these is going to be the best base, or do you think they're about the same? It's a little bit tricky to think about. Size doesn't matter for basicity. So if I wanted a good base that is a bad nucleophile, I might pick this one. So we can try to find something that's exclusively a good base but not a good nucleophile, meaning it won't do substitution chemistry readily. All right, last but not least, let's finish up just going over factors that affect delta G, meaning basicity. We said stability matters. Whoops. And really this follows the cardio rules. Another way of describing this is it follows them poorly, right? We want our negative charge to be on a non-electronegative atom, or we want it to be on a small atom or something like that. So we can follow all of these rules for stability. And then next thing we think about is we want our base to form a stable / non-acidic conjugate acid. So we can look at the acid as well. But the big note here is that sterics and solvation don't matter much. Does that make sense? All right, so what we're going to do is we're going to stop here today, and then when we come back on Monday, we'll kind of go through and we'll make a good chart of things that are good nucleophiles only, things that are good bases only, things that are good nucleophiles and good bases, and things that are just crummy nucleophiles and crummy bases. So we'll try to segment this out.